So we will wait for a few more minutes for people to join. We'll start after that. I hope I'm audible and the screen is visible, the file which I'm sharing. If you can please answer. week 2 session for mechanical measurement system for problem solving sessions. So first question is, the smallest measurable input is called A. resolution, B. drift, C. threshold, and D. precision. So the answer for this one is threshold. So threshold is the initial starting how much energy which is needed for the measure instrument to give you an output. So that is called the threshold. Precision is how the values which the instruments gives you output, which how close they are, that is defined by precision. And we'll see the next question. The smallest measurable input change is called, the previous one if you remember, it's called the smallest measurable input, but so the question 2 is smallest measurable input change. So the smallest measurable input change is called A. resolution, B. error, C. drift, D. hysteresis. So the answer, I'll repeat, the smallest measurable input change is called A. resolution, B. error, C. drift, and D. hysteresis. So in this case the answer is A. resolution. So for the instrument it could be the least count as well. The resolution is the minimum input, the variation in the input which gives you the output. So the output is can be the least count of the instrument as well. So that defines the resolution of the system. As you know, error is the difference between the indicated and the true value of the reading. So if you want to measure a temperature, the actual value is 100 and your instrument shows you 101 or 99. So in this case the error is 1. So drift is how the input is over the course of time, the instrument may at 0 input also will have some other reading. So that is called as a drift. And the hysteresis, for a given input it can have 2 outputs. It will behave differently while loading and unloading. So that phenomena is defined by the hysteresis. So the smallest measurable input change in this case is resolution, while the smallest measurable input is the threshold. So that threshold is the minimum input which you used to give so that initial output is visible. So that is threshold, and the minimum change to see the output is the resolution. So the third one, you see, the linearity of an instrument signify A. minimum error in measurement, B. highest error in measurement, C. linearity has nothing to do with error in measurement, D. linearity is a function of error in measurement. So I repeat the question. The linearity of an instrument signify minimum error in measurement, highest error in measurement, C. linearity has nothing to do with error in measurement, D. linearity is a function of error in measurement. So in this case the answer is C. linearity has nothing to do with error in measurement. So the linearity signifies the relation between the input and output of an instrument. So in this case the linearity has nothing to do with the error as such of the measurement. So I'll repeat the question. The linearity of an instrument signify minimum error in measurement, highest error in measurement. Linearity has nothing to do with error in measurement. Linearity is a function of error in measurement. So the option 4 is this is linearity has nothing to do with the error in measurement. Next question. The ratio of the output to input change for a given measuring system is referred to as A. Sensitivity, B. Linearity, C. Stability, D. Fidelity. I repeat, the ratio of the output to input change for a given measuring system is referred to as A. Sensitivity, B. Linearity, C. Stability, D. Fidelity. The answer for this is sensitivity. So any system, how sensitive the system is defined is the amount of uh, in change in the output which caused by the input, that is defined as sensitivity. So if your output is a large for a small amount of input, the system is highly insensitive to that input. The input can be of anything. So if you want no the input is not, it's as an interfering input. If you want to measure temperature, or per se if you want to measure pressure, and if your instrument is sensitive to temperature, so the readings may change. So you have to take into account that the instrument is not sensitive to the interfering input. Or if you want to per se if you want to measure voltage or a current ammeter, and if you have a magnetic field around the readings, and if you have an analog type voltmeter, so the needle can have a error in reading because of the magnetic this thing. So this instrument is sensitive to the magnetic field. So we need sensitivity of the uh, input which has to be measured. So higher sensitivity to take care of the input to be measured. So the sensitivity is defined as the ratio of output to the input change in output by change in input. That gives you sensitivity. Next question. A flow meter having a range of 50 to 250 meter cube per second has guaranteed accuracy of plus or minus 0.75% above 25% of scale range. If the instrument indicates 160 meter cube per second, then the static error will be, I repeat, a flow meter having a range of 50 to 250 meter cube. A flow meter having a range of 50 to 250 meter cube per second. So you have a flow meter, you have to measure some flow. So the range in which the flow meter can measure is from minimum of 50 meter cube. So the minimum flow rate which you can measure is 50 meter cube per second, and the maximum is 250 meter cube per second. So it has a guaranteed accuracy of plus or minus 0.75% of above 25% of scale range. So it has a 0.75% of accuracy. So above 25% means we have above 50, the range 50 is scale is 50 minus 250. So a flow meter reading can be minimum is 50 meter cube per second, and a maximum is 250 meter cube per second. So it says about 25% of the scale range. Scale range is you have 250 minus 50, so 200. So 225% of that is you have 50. So above 100 meter cube per second, the measurement will give you a percentage of plus or minus 0.75% accuracy. So in this case, the instrument reads 160 meter cube per second. You have been asked to calculate the static error. So I read a flow meter having a range of 50 to 50 meter cubes. Okay, so that is the range in which the flow meter can measure. It has an accuracy of plus or minus 0.75% above 25% of scale range, so above 100 meter cube per second. So now the indicator reads 160 meter cube per second, which is above 100. So you can use the plus or minus 0.75% to calculate the error in the measurement. As you can see, the answers options are 1.5, 1.2, 0.75 and 0.3, out of which the answer is B. You see, about 25% scale is 100 meter cube per second. So indicated is 160, so which is above 25. So error will be plus or minus 0.75 into 160. As the percent it's in the full scale reading, so it will remain 0.75 to the true value of the indicated measurement which is indicated. So 0.75 into 160 by 100, which gives you plus or minus 1.2 meter cube per second. So the reading can be 161.2 or 158.8. So that is the reading which you can have the flow measure for 160 meter cube per second. So moving to the next question. Due to loading effect during measurement, the instrument output is A. decreased, B. increased, C. unchanged, D. none of the above. So due to the loading effect during measurement, the instrument output is A. decreased, B. increased, C. unchanged, D. none of the above. So in this case, if you see, loading effect occurs if the instrument which is used to measure puts an additional load to the system for in which the value has to be measured. So it acts as an additional load, so that the load is called the loading effect. So per se, if you want to measure a temperature of a certain fluid, and if you have a beaker and you have some fluid in that, and at certain temperature T, if you want to take a normal thermometer, and it itself has a certain huge mass, and if you dip it in the fluid, it can take certain amount of heat to heat itself. So the measurement in the reading will be different with the actual temperature measurement. That it's the thermometer will put an additional load to the system in which the temperature has to be measured. So that acts as a loading effect. So if you, in this case, the instrument output will decrease because the additional load is put by the instrument. So the answer will be A. So due to the loading effect during measurement, the instrument output is decreased. So next, which of the following expresses the central tendency of data? Which of the following expresses the central tendency of data? A. mean, B. mode, C. median, D. all of the above. I repeat, which of the following expresses the central tendency of data? A. mean, B. mode, C. median, D. all of the above. So central tendency is in the statistical analysis the central part of kind of an averaging to take an estimate of how distributed the data is, to see the central value. You can use either three of it. So the answer is D. all of the above. If you see, mean is the average value of the data which you have, if you have a spread of data, so you sum it all and divide it with the number of the data readings you have. That will give you the mean. The median is the middle value of the list order. So if you try to put it in an ascending order, you have the middle value, the middle value of the data, that will give you the median. The mode is the most frequently which the data is you get. If you have a spread of data, you see if you have 100, 200, 250, then 200, then 300. So in this case, the 200 is the median. Mode. So the more frequent the data is, that is defined by the mode. Mean is the average value, and the mean is the average value of that. Median is the middle value. So the central tendency of data is all three. You can use all three for the central tendency of data. So which of the following expresses central tendency of data is D, all of the above. The following readings are taken of a certain physical length with the help of a micrometer screw. So a micrometer screw, and you are estimating a physical length of certain system. So your readings are 1.41, 1.45, 1.63, 1.54, 1.49, 1.51, 1.60, 1.55, 1.47, 1.66 mm. So the average deviation and variance respectively is calculated. So you have a micrometer screw which is used to calculate a certain length of a system, and the readings are given. So you have 10 readings of the system which is measured. You have 10 readings of that, and you have been asked to calculate the average deviation as well as the variance of the data. So if you see, you have 10 observation listed, and you have the lengths measured which are listed. So first is 1.41, 1.45, 1.63 as per the given value, 1.3, 1.66, the 10th reading. Then you have to calculate the deviation. So how do we calculate the deviation? So for calculating deviation is the true value minus the mean value. That's how the deviation is calculated. So you have the 10 readings, you sum it all up, so you get 15.31. So divide by 10 readings, you have 10 readings. So add all 10 readings, 1.41, 1.45, 1.63, you sum it all up till 1.66, divide by 10. So that gives you 1.531. So the deviation will be the true value, the length which is measured, minus the mean value, that is 1.531. So initial first one is 1.41 minus 1.531, which gives you minus 0.121. Like that, the next 1.45 minus 1.531 is minus 0.081. 1.63 is 1.63 minus 1.531, which is 0.099, and so on and so forth till you see 1.6 is 0.123. That's the deviation. So if you see, if the values which are less than the mean are negative, and which is greater than mean are positive. So the deviation, how much the value is deviated from the mean value, that gives you the deviation. And if you see the square of the deviation, it's you have to square the values of that. So 0.121 square is 0.0146 141, and 0.081 is 0.00656, and so on and so forth. If you take the summation of that, of the deviation, it's 0.65, and if you take the summation of the deviation square is 0.0586. So next, to calculate, as you said, the arithmetic mean is being calculated, which is the sum of all values, then 15.31 by 10, which is 1.531, which was used to calculate the deviation. Then if you see the average deviation, which has been asked, you have been asked in data, you have been asked to calculate the average deviation and the variance. So how do you calculate average deviation? Average deviation is summation of all the absolute values divided by the total number of readings. So you have if you have minus 0.121, you have take 1.121. So you have to take the absolute values of all the readings, sum it up. So that gives you 0.65. divide by 10, so that gives you 0.065. So the average deviation from the value is 0.065. So the total spread, the average value, if you take an approximation, that the values are spread from the mean value by 0.065. So then how next is the calculation of variance. So sigma is the standard deviation, so variance is standard deviation square. So if you the standard deviation is summation of the deviation square, or a summation of x minus x mean, the square of that, divide by n minus 1 raised to power 1 by 2, or square root of, take the summation of x minus x mean the whole square, which is the deviation. X minus x mean is the deviation, so square of the deviation, which is written summation of deviation square by n minus 1 raised to power half. So here we have been asked to calculate variance, which is the square of standard deviation. So sigma square equals the square of the standard deviation values. So you know, from the deviation square you get 0.0586 divide by n minus 1. So n minus 1, n is 10 here, so n minus 1 is 9. So 0.0586 by 9 is 0.00651. So the average deviation is some absolute value by n, absolute value summation of all deviation by n, which is 0.065. And if you see variance is summation of deviation square by n minus 1, which is 0.0586 by 9, which is 0.00651. And if you see that units are, deviation is in mm and variance is in mm square. Moving on to the next question. A new cure is made for a certain type of ceramic sheet which changes the mean compressive strength. A total of 15 samples of ceramic sheet have been tested, and the observed mean of the samples is found to be 545. Find the 99.7% confidence interval for the mean. Take standard deviation of 75 kg per centimeter square and assume normal distribution. Take confidence interval at 99.7 as 3. So you have, I'll repeat, a new cure is made for a certain type of ceramic sheet which changes the mean compressive strength. So there's a ceramic sheet, and a cure is made which will change the compressive strength of the ceramic sheet. So you have 15 samples of the sheet, and after testing, the observed mean is, or the mean of the 15 samples, you have the data for the 15 samples which has been tested for the compressive strength, and those data's mean value is given as 545. And you have been say that find the 99.7% confidence interval for the mean. So the data are normally distributed. If you see, if 100% is the total area probability of that, so 99.7% is the 3 sigma values. And take standard deviation, they have given standard deviation as 75 kg per centimeter square, and to assume it was a normal distribution, and they have given for confidence interval of 99.7 as 3. So if you see, the mean value of 15 samples is the mean xm is 545, and 99.7% confidence interval for mean is, if you see, for confidence interval x at the 99.7 values are xm plus or minus z sigma by root of n. So if you see, the x 99.7 is, you have a mean value, you have a bell curve, the highest peak value is where the mean lies, and you have to calculate the 99.7 intervals which are the extreme 3 sigma values, or both sides you will have a plus, that's why you have a plus or minus sign from the mean value, and z sigma by 3 gives you that 3 sigma values for the 99.7% confidence level. So the xm plus or minus z sigma by root of n, and you know, for 99.7% z is 3, and sigma standard deviation is given as 75, and n is the number of samples, or the number of data points for observations which has been made. So n is 15 here, you have 15 samples for which the mean has been calculated, so n is 15. So if you substitute the values in the above expression, so you have x is 99.7 is 545 plus or minus 3 into 75, the standard deviation 75, divided by root of 15. So 545 plus or minus 58.09. So that gives you the interval in which the 99.7% of the data values lies are 603.09 and 486.91. So those are the compressive strengths interval. If you move on to the next question, you have a pressure gauge having a range of 100 to 1000 kilonewton per meter square, which has a maximum error of 0.2% of full scale. FS full scale. What would be the possible readings for a true value of 250 kilonewton per meter square? I repeat the question. A pressure gauge having a range of 100 to 10,000 kilonewton per meter square. So you have a pressure gauge, you have to measure pressure. So that pressure gauge, the minimum value is 100, the maximum pressure which you can measure is 1000 kilonewton per meter square. So that is the range in which the pressure can be measured. This is scale values, and which has a maximum error of 0.2% of full scale reading. So the error will remain throughout the readings, and it is at full scale. If it's at true value, the indicated value, you use the indicated value to calculate the readings. So we have been asked what would be the possible readings for a true value of 250 kilonewton per meter square. So as the maximum error is for full scale, so it will remain 0.2% throughout throughout the reading. So 0.2% of the full scale is, you have a range of from 100 to 1000. The scale is 1000 minus 100, you have 900. So 0.2% of that. So 0.2% is 0.2 into 1000 minus 100 divided by 100. So that gives you 1.8. So the plus or minus 1.8, that is the maximum error which you can have. So this plus or minus 1.8 kilonewton per meter square. Please note that's kilonewton per meter square. So error is plus or minus 1.8 kilonewton per meter square. So the error will remain same for throughout the scale readings, whatever may be the true values. So if the error is given a true value, instead of 1000 minus 100, you have to use the true value there. So if it would have been, the question would have been the pressure gauge having so and so error of 0.2% of true value, then it would have been 0.2 into 250 by 100. So you would have calculated that. So it will be given point plus or minus 0.5. In this case, it has been said it has been full scale. So you use the scale 1000 minus 100 into 0.2 by 100. So that gives you plus or minus 1.8. So in the case of true value, they are asking what would be the possible readings for a true value. So the possible readings can be 250 minus error or plus the error. It could be either of that. It could lie in that interval. It's 250 plus or minus 1.8. That could be the interval where the true value of 250 can be indicated. So the possible readings of the true values will be 251.8 or 248.2. So whichever lies in the readings, 251.8 to 48, that can indicate a 250 as the true value. Moving on to the next question. From the following data, find, you have given a data y and x, 1.2, 2, 2.4, 3.5 and 3.5, and x is 1, 1.6, 3.4, 4, 5.2. A linear relation between y as a function of x, and you have to also been asked to find correlation coefficient for this case. So you have a data y and x which is given. You have to find a relation between y and x, and also see how good the relation of y and x, the data with the data. So that is calculated by the correlation coefficient. So as you see, if yi is 1.2, 2.4, 3.5, 3.5 as given in the data, and xi listed 1, 1.6, 3.4, 4 and 5.2 as per the data, you calculate xi and yi. So that gives you 1.2, 3.2, 8.16, 14 and 18.2. This multiplication of the xi and yi values. So 1.2 into 1 is 1.2, 2 into 1.6 is 3.2, 2.4 into 3.4 is 8.16, 3.5 into 4 is 14, 3.5 into 5.2 is 18.2. And the next is you also need xi square. So you square the xi values. So you have 1 square is 1, 1.6 is 2.56, 3.4 square is 11.56, 4 square is 16, 5.2 is square is 27.404. Now you sum all the values of yi, xi, yi and xi square. So if you have this, please note that this is done by least square. So we are solving it as a least square to fit the yi and xi. So we have summation of yi is 12.6, summation of xi is 15.2, and summation of xi yi is 44.76. You add 1.2, 3.2, 8.16, 14 and 18.2, you get 14.76. Same with case of xi square. You add up all the 5 values, you get 58.16. Now assuming that this has a linear relationship, that y and xi has a linear trend, it's a line defined by y equals to ax plus b. You have n equals 5, you have 5 readings, and you are fitting this 5 into a linear line. So in that case, as you can remember, in the least square, you try to minimize the error between the data and the curve which has to be fitted. So is y minus yi indicated. So and y is replaced by axi minus b, and when you differentiate this with respect to the variables a and b, you get two equations, and while solving the two equations you get a relation for a and b. So the a is n summation of xi yi minus summation of xi into summation of yi divided by n summation of xi square minus summation of xi the whole square. As you can see, we have already calculated summation of xi yi, summation of xi, summation of yi, and summation of xi square. So we have all the values required to calculate the a and b for the linear line. So substituting all the values for a, 5 into summation of xi yi is 44.76 minus summation of xi is 15.2 into summation of yi is 12.6 divided by n is 5 into summation of xi square is 58.16 minus summation of xi the whole square is 15.2. Your summation of xi is 15.2, the 15.2 whole square. So if you will get 0.54, so a value is 0.54, and the next b, so y equal to x plus b, you have already find out a. So finding b is summation of yi into summation of xi square minus summation of xi yi into summation of xi divided by n summation of xi square minus summation xi the whole square. You see the a and b are somewhat similar in the expression. So and then you use the b value, substitute all the values which are already found. So you go summation yi is 12.6, so into 58.16 is summation of xi square minus 44.76 is summation of xi yi into summation of xi is 15.2 divided by n is 5, summation of xi square is 58.16 minus 15.2 the whole square. So that will give you 0.8779. So now we have found all a and b. Now the linear for the line, we had two variables a and b which has to be found. So we have already found that. So which will give you the relation of the x and y for a line is y is 0.54, x plus 0.8779. So the data using least square method, we have fitted a line which gives you a relation for this x and y, and we expected that this will fit the data perfectly, or like may not be perfect. So how good the fit is, we will find using the correlation coefficient. So for calculating the correlation coefficient, you find the mean value of y, which is summation of yi by n. We have already found out summation of yi is 12.6, So 12.6 by 5, which is 2.52, and we find the indicated values. So we have y, relation y of the line which have been fitted. So we substitute all the x values and we find the yi values. So we have, when you find yi values, it's 1.419 for x equals to 1. You substitute x equal to 1, you will get 1.419, and same with x equal to 2, we get 1.743. For x equal to 3, we get 2.715. For x equal to 4, we get 3.309. For x equal to 5, we get 3.6. So x equal to 5.2. Sorry, you substitute x values. So x is initially is 5.540 into 1, and then plus 0.87, that gives 1.419. Then xi value is 1.6. You substitute 1.6 here and we find out it's 1.743. Then we substitute x equal to 3.4. If you substitute 3.4, you get 2.715. Then you substitute 4 and then you substitute 5.2. You get y indicated values, and yi is the reading value which is already been given, for which the line has been fitted. So you take the difference between these two, the values represented by the line as indicated by yic, and the values data which was used to fit the line, that indicated by y. So the difference between those is given as yi minus yic. Square of those is 0.048, 0.06, and 66.0992, and if you have take the summation of that, you get 0.4607. So the standard deviation in this case is summation of 0.4, the readings divided by n minus 2. So to use that, you get 0.03919, and you also need to find sigma yi, sigma y. So r is relation is 1 minus sigma yx the whole square divided by sigma y square the whole raised to power 1 by 2. That is the r relation. So we have found out sigma yx, which is summation of yi minus yi indicated the whole square divided by n minus 2. So that is 0.3919. We also need to find sigma y value. Sigma y is summation of yi minus mean value. We have a mean value, we have calculated 2.52. That minus y minus y mean the whole square divided by n minus 1. So we have to find 1 minus 2 minus 2.52 the whole square of that. Same with 2 minus 2.52 the whole square, 2.4 minus 2.52 the whole square, 3.5 minus 2.52 the whole square. Same for 3.5 minus 2.52 the whole square. The summation of all this, and then divide by n minus 1. If we do that, we'll get sigma y square. So sigma y square, we'll get sigma y square. In this case, the root of that will give you sigma y, which is 0.987. So to find out correlation r is 1 minus sigma yx square by sigma y square raised to power the whole raised to power half, or square root of that. So we can say r square is 1 minus sigma yx square by sigma y square. So we know sigma yx and sigma y, you substitute that, so we'll have 1 minus 0.3919 divided by 0.987 the whole square, and the square root of that. We'll have r is 0.9178. So we can say it's close to 0.91. So it's a fairly a good fit. Not that great, but the good can go with a different relation to have a better fit. So the next question is on impedance matching. We have a circuit here, and so the two terminal device shown in figure has an internal resistance of 5000 ohms. The two terminal device shown in figure has an internal resistance of 5000 ohms, a meter with an impedance of 20,000 ohms is connected to the output to perform a voltage measurement. What is the percent error in determination of the internal voltage? So we have been asked to find the percentage error in finding the internal voltage. So we have a two terminal device. The two terminals are A and B. It also has an internal resistance of 5000 ohms. So the internal resistance Ri. Uh, so we have a voltage across here which has to be measured, and we have internal resistance of the instrument which is Ri of 5000 ohms. So of the system, and we are putting up a load and we are measuring the voltage across. So we have an impedance of 20,000 ohms which is connected. So the load is 20,000 ohms is connected to the output to perform a voltage measurement. You have to find out voltage across AB. So what is the percentage error in determination of the internal voltage? Because of this internal resistance, what could be the error in the voltage measurement? That's what we've been asked. So if you find the relation between the voltage across AB and the E which is being measured, the terminals is E AB will be E into R by R plus Ri. So if you see this internal resistance and the load are in series, you see, and if you find out the current across the circuit is for voltage measurement EAB is EAB by R. So this will be equal to the current across the whole circuit. If you see, the whole total resistance will be R plus Ri, and the voltage across the terminal including both the resistances will be E. So E by R plus Ri will be equals to the current here EAB by R. So from there we can find the relation EAB equals E into R by R plus Ri. So we know the relation between the voltage across the load and the total voltage measure. So the error in this measurement is 1 minus the E or you can say the measure E minus EAB by EAB E. So or you can say 1 minus E by EAB into 100. So delta the difference in the voltage or of the actual voltage which I measured is E. So E minus EAB. EAB is the internal voltage of the terminal, and divide by E. So that is the percentage error of the measurement of the internal voltage. So you use the relation between EAB and E, you get a relation R by R plus Ri minus R divided by R plus Ri into 100. That gives the percentage error in the voltage measurement. So we know this will turn out to be Ri by R plus Ri into 100. Ri is the internal voltage and R is the load resistance. So if we substitute, we know Ri is 5000 ohms and R is 20,000 ohms. If we substitute, Ri is 5000, R plus Ri is 5000 plus 20,000, which is 25,000 into 100. This will give you 20%. So there will be a 20% error in the voltage measurement. So moving on to the next question, you have a device in the previous problem, the same problem, this thing. We have as an internal voltage of 100 volts. We have an internal voltage which is 100 volts. You have to calculate the power output for the loading condition indicated. So you have to calculate the power output of this case, and we have been asked what can be the maximum power output. So the maximum power output which can be transmitted to the load, that has to be calculated, and what power output would result for a load resistance of 1000 ohms. So if your load resistance is of 1000 ohms, what could be the power output result? So the question is in 3 parts. We'll see. In the first part, we know the relation between the internal voltage and the total voltage. So EAB is E into R by R plus Ri. If you see, power is voltage into current, and we know current across EAB is EAB by R, and into voltage, so EAB square by R. So EAB, if you substitute EAB relation, we get E square by R into R by R plus Ri the whole square. So we have the power relation between power, the voltage and the resistances. We know that E is 100 volts, which is given the device in previous problem. This has an internal voltage, E is 100 volts. We have to calculate the power. So we have E is 100, R is 20,000 ohms, and Ri is 5,000. The same as per the previous problem. We have R 20,000, R is 5, Ri is 5,000. So substitute that, we have power is 20,000 by 25,000 the whole square into E is 100 square by 20,000 square 20,000. So this gives you the power of 0.32 watt. So for the present case of 5,000 internal resistance of 5,000 and load of 20,000, we have a power output of 0.32 watts. And the next question is, what would be the maximum power output? I expected to ask what can be the maximum power that can be transmitted. So that can only happen when power is at the maximum, and we can change the load. We have the internal resistance cannot be changed, so uh, we can change the load to for the maximum power which can be transmitted. So for P being a maximum and the variable being R, we differentiate the power with respect to R. So when we differentiate, what we get is R equals Ri. So when both the resistance are equal, that's the case when we can have a maximum power transmission. So Ri is 5,000 ohms, so R is also will be 5,000 ohms. So when we substitute R equals to Ri, we have R by 2R the whole square into E square by R. So R gets cancelled out, so you have used E square by 4R. So when you substitute E is 100, 4 into R is 5,000 ohms, so you get 0.5 watt. As you can see, when the resistance of the load comes down from 20,000 ohms to 5,000 ohms, the power has increased from 0.32 to 0.5 watt. So the next part of the question is, what power output would result for a load resistance of 1000 ohms? So they have said what power output would result for a load resistance of 1000 ohms. So for load being 1000 and internal resistance being same as 5000 ohms, we substitute the previous relation, the same relation, E square by R by R plus Ri the whole square. We get power as R is 1000, so 1000 by R plus Ri is 5000 plus 1000, which is 6000. So the whole square into E square is 100, E is 100 volts, so 100 square by R is 1000, so 100 square by 1000. So this gives you 0.272 watts. So you can see when the R has gone down, so the power has also gone down to 0.278 watts. It's close to the previous of 20,000 ohms. So this power will goes through the peak at R equal to Ri of 5000, and it reduces at the either side if you increase the resistance or decrease the load resistance. So for maximum power transmission, you need to have R equals to Ri, as you can see from the values. Moving on to the next question, we have a certain power supply stated to provide a constant voltage output of 10 volts within plus or minus 0.1 volt. So the output is assumed to have a normal distribution. So there is a normal distribution, and the probability that a single measurement of voltage will lie between 10.1 and 10.2 volts. So we have a power supply which gives you a constant voltage of 10 volts and within accuracy or error of 0.1 volts uncertainty, and the output is assumed to have a normal distribution. So the output is we are assuming a normal distribution of the output. So we have to calculate the probability that a single measurement of voltage will lie between 10.1 and 10.2 volts. So as you can see, this being a normal distribution, there will be a bell curve, and the mean value will be 10. We are expected to calculate probability in the interval of 10.1 to 10.2. So you have a mean value of 10, we have a 10, no, that will be a bell curve, you have a 10.1 and we have a value of 10.2. The area under that region will give you the probability. So we'll use, this is a normal distribution, we'll see. So for this case we have a standard deviation of plus or minus 0.1 volts. So your value is 10 volts, but it varies between 0.1 volt, so the standard deviation will be plus or minus 0.1 volts. So probability that the voltage will lie between 10 and 10.1 volt is plus 1 sigma, and the probability that it will lie between 10 and 10.2 is plus or plus 2 sigma. So you have a normal the bell curve, the either side will give you plus or minus. We need a interval between 10.1 and 10.2, so we only consider the positive regions, so plus 1 sigma. So the probability of P being plus zero point 0.1 from the table for the normal distribution, we calculate that it will be 0.34134. So, and while the probability that it will lie between 10 and 10.2 is, for the 2 sigma value, is 0.47725. For this normal distribution, probability you from the table, you have a value for normal distribution eta, which is defined by x by standard deviation. So you have to substitute, and then x is 10.1 divide by 0.1, so that will give you the eta values, and you find the probability there. So, and from the table, if you see, so for error function, if it will give you for probability of 1 is 0.34134, and probability of 2.2 is for 2 sigma, the sigma values. So you take eta will be 1 and 2. Of course, it's a sigma values varying from 1 sigma to 2 sigma. So the eta values will be 1 and 2, and from the table, so if you find probability for 0.1 is 0.34134, and for 2 is 0.47725. So this probability gives you the area from 10 to 10.1 in the bell curve. 10 is the mean, and 10.1 you have an interval. So from 10 to 10.1, the area under the bell curve will give you the probability. So that is 0.34134, and you have another area or probability between 10 to 10.2, so that is 0.47725, and you have been asked to find the probability between 10.2 and 10.1. So what we do is the probability of 0.2 minus the probability of 0.1, so that is 0.47725 minus 0.34134, so that gives you a probability of 0.13591. So the probability that your measurement voltage will lie between 10.1 and 10.2 volt is 0.13591. So moving on to the next question, we have a data taken from a certain heat transfer test. You are doing a heat transfer test, and you are expected to have a correlation that y is equals ax raised to power b. So you have to use a least square method to obtain a best correlation for this. You have x values and y values listed. It's a 20 to 2040 to 580, 2980, and so on and so forth. And you have y values for the corresponding value, 33.2, 32, 42.7, and so on. You are expected to calculate the mean deviation for this data for the best correlation. So you have to use the least square method. So in this case, what can do is y equals ax raised to power b. So you apply logarithms on the both sides. You have ln y equals ln a plus b ln x. So when you find that, you have listed y values, you have listed x values, and in this case ln y will become y, ln x will become x, ln a you can assume it as capital A or something. So you have ln y, logarithm of y values, so you take logarithm of 33.2 is 3.5 and so on and so forth, and ln x you take a logarithm of x, so you have 7.63 and so on. So you have a different x and y value. This is just converting it to a product problem into a simpler linear problem. And you have square of ln y y, and it is square of ln x. You have square of ln y ln x. So we have all those readings, and we find out 3.4713 for the mean value, and mean value of ln x is 7.67. The mean value of ln y square is 12.44. The mean value of ln x square is 59.05. The mean value of ln y and ln x is 26.82. So we proceed to find further. This case it's a slightly different approach. This is similar to what we did in the previous case. In this case, so the relation a and b, this can be expressed in terms of sigma values. That's what has been done here. We are finding a and b in terms of sigma values, and here the sigma y square is calculated is y square minus y mean mean value of the y square minus the mean of y the whole square, that is sigma square y. And we know the mean value is calculated already here. We know the mean of y square is 12.4438, and minus the mean of y the whole square, that is 3.4713, the square of that. So that will give you sigma y square as 0.3936. The same is for sigma x square. We calculate sigma x square, which is x square mean minus x mean the whole square. So in this case we'll have sigma x square mean is 59.05, and the same x and y are ln x and ln y respectively, and the sigma x mean the whole square is 7.6753 whole square. So that will give you a sigma x square value of 0.1399. So you have sigma xy, which is xy mean minus x mean into y mean. So when you substitute the xy mean, it is 26.8251, and summation of x mean is 3.4713 into y mean is 7.6753, which is 0.1818. So the b value for relation here, it's so here b value is the sigma xy minus by sigma x square. So you have sigma xy is 0.1818, which we have calculated, divided by 0.1399 for the sigma x square. So you have 1.299 for the b value, and we have substitute the b value here and the mean values of y. So to find out the remaining constant ln a, so if you have y mean minus b into x mean, so you have y mean is 3.4713 minus 1.299 for the b value which we have calculated, into the x mean value 7.6753. So that will give you ln a as minus 6.4989. So you have found out ln a. We need a from the for relation y equals to axb. We have found out b 1.299. So a is 0.015. In the question we have been asked to find out the mean deviation. So if you see the mean deviation is you find out the yc, the indicated value of the curve. You see yic, that you substitute the x values 2040, 2580 and so on to find out the respective y values. So when you substitute in the y equals to ax b relation, you know a is 0.0015 and b is 1.299. You substitute x is 2440, you get 29.8745, and same 2580 if you substitute 40.53. You calculate for all y values, and then the difference between the actual y value and the calculated y value. So the deviation is 33.2 minus 29.87451, which gives 3.32, and same 32 minus 40.53, which gives you minus 8.53. Calculate all the deviation, the absolute values of the deviation, sum all the deviation values and divide by the total number of readings, you get the mean deviation. So that is 12.9562, which has been asked to calculate. So the next question is, it's a chi-square test to calculate a hypothesis whether this is true or not. So in this case, it is suspected that the rejection rate for a plastic cup molding machine is dependent on the temperature at which the cups are molded. So a series of short tests is conducted to examine this hypothesis with the following results. You have a temperature, 4 temperature, and the production has a certain number of production, and out of the production some are getting rejected. So you have 2 which is given in production, and you have a rejection rate. On basis of this data, you have to agree whether the hypothesis is true. So the hypothesis is that the rejection is dependent on the temperature. So you have to test how we test this. So for this we have to apply a chi-square test. We have f freedom is n minus k, n is 4 and k is 1 for the restrictions. So you get f is 3. So the expected rejection rate is 43. The total you have number of rejection is 43, and rejection by the mean total production is 545. Your production for all the cases, you have sum it up, you have 545. The total number of rejection is 43. So the number of non-rejected will be 150 minus 12, which is 138. The same you find all for all non-rejected. So the number of non-rejected will be 502. So the expected non-rejection rate is 502 by 545. So that will give you 0.921. So the expected rejection rate is 0.079, and the expected non-rejection rate is 0.921. We do a chi-square test, and the chi-square value is the actual observed value by expected value, the whole square by expected value of the summation of all them. So you have the observed value is 12, so 12 by 150. The rejection rate is 12 by 150. You have 12 by 150 minus the expected value is 0.079. So you put the expected value, the whole square by expected value, which is 0.079. Same for the second one. We have 8 rejections, so the rejection rate is 8 by 75 minus the expected values, and so on for the all 4 readings. And then the non-rejection rate is 0.921. So the expected is 0.921, and we are actually observed is 138 by 150. So 138 by 150 minus 0.921, the whole square, divided by the expected one for all 4 into 10 power minus 4. So that's a mistake. Not 3 is not here. So just a second. So if you substitute all the values and calculate, you get 0.1266 plus 96.89 for all the individual values. When you sum it up, and you get 0.0135. The chi-square value is 0.0135. So from the table, we get for 0.0135 and freedom of 3, we find out what is the probability. So that probability will be greater than 0.995. So which is concluded that the rejection rate is dependent on the temperature. As the probability value is greater, it's the relation is good. So it is assumed that the rejection rate is dependent on the temperature. So that's all for the today. If you have any doubt, you can ask. You have any query? Am I audible? Uh, Prem, you have raised your hand. If you have any query, you can ask. Prem, do you have any doubts, or else can close the session? Kindly respond. So I may know. You have raised your hand. So am I audible? Do you have any query? I'll ask again. Do you have any query? If you can have any query, you can continue, or you can close the session. So I hope you have no doubts. If you have a doubt, you can ask now, or else I'll close. I'm waiting for your response. So I hope you don't have any query. I'll close the session. Thank you.